We're going to review what a closed system is in thermodynamics. In the first law of thermodynamics, energy problems, the simplest type of problem is a closed system or a no-flow system. Some people call that a control mass system. I don't, but I call it a closed system or no flow. So basically, m dot equals 0 is what I would write at the top of my paper if I were to get a closed thermodynamic system. It means that the amount of mass is fixed, no mass flow. No mass flow. Remember, the dot means flow, m means mass. No mass can cross that boundary. So here you have a boundary. The first step in any thermodynamics problem is to define a system and its boundary. So here we have our system, and we see that m dot equals 0. No mass flow. We also have to recognize this is the boundary. And that is a system where nothing happens. Now, it is saying that the mass is, of course, it makes sense that the mass is constant in here. Mass is constant because no mass is coming in, no mass is coming out. That's great. But it also does say here that energy, let me just switch my color here so that we can talk about energy. I like doing energy in red. Energy, yes. So that's saying that energy can cross this boundary. Well, what kind of energy crosses a closed boundary like that? If this were just, a pressure vessel, for example, just a volume, what kind of energy can go into and out of a constant volume? This looks like a constant volume. This does not look like a piston is pushing up and down on it, changing the volume. This looks like a constant volume process. One type of energy that can go in is heat energy. Heat energy can go in at a rate. That's why there's a dot. Heat energy can come out. Q energy can come out. Heat energy can come out. So here, heat is acting on the system by the surroundings. Here, energy is acting on the surroundings by the system. This is heat energy by the surroundings on the system. And we sometimes have both of these going on. This is by the system on surroundings. And this is closed. So what is an application like that? Okay, well, what could be happening? Here's what could be happening. This could be sitting in the sunshine of today, and it could be very, very hot out here. And it could be cooler here. And that means that heat energy is going to transfer from the higher energy to the higher quality energy to the lower quality energy, and it is getting warmed up. So this could be just warming up. This could be warming up. And then the fact that this is not very insulated, we could say not a Yeti. This is not a Yeti. It's not very well insulated. Therefore, it's losing some of that heat once it warms up, maybe. But although that's kind of weird because it wouldn't, would it? Because it's hotter outside. So at that point, I'd have to have like half of it inside cold environment, and then this is hot in order for Q to transfer over there. So I don't even really like where this example has been going. And I think I want to erase it and do a different kind of example, a different illustration. I wouldn't say it's an example at all, but this diagram is saying energy can, yes, transfer the boundaries. And I want to do an illustration of energy transferring these boundaries from the system to the surrounding or from the surrounding to the system. You get what I say about the heating up there. Then some losses can come out of something as well. But let me give you a different example. If I take this closed system And then I do some work on the system. Remember, the system is the stuff inside here. It's the stuff inside here that I can quantify. I can calculate it. I can, like, it has a constant mass. That mass is measured in kilograms. There's a mass of something in there. It's a solid or a liquid or a gas. Normally it's a liquid or a gas. I'm going to do some work on it. I want to do some mechanical work on it. So as my illustration, I'm going to do some mechanical work. How can I do some mechanical work? Well, maybe I mix it up. Mixing it up actually puts some energy into this system. So this is a mixer. And the mixer adds energy. So it does work. And so what this is doing is the surroundings, SU, surroundings do work on the system. And you really have to get this straight. A mixer here is doing work on the system. It's not the system doing work on the surroundings. Okay, the system is a fluid. The fluid's not doing work on the surroundings. The fluid isn't making that mixer turn. But in the case of a turbo machine, the fluid typically makes the machine turn. So that's entirely different. Pretty neat. So this is going to do work on the system. And now there's more energy in the system, right? So now energy is increasing, but can energy be created or destroyed? No. There's more energy in the system. Well, that energy is going to go somewhere. That energy is going to go somewhere, and it's probably going to be more excited particles, and it's probably going to warm up. We're going to get an increase in temperature in here. And so since I'm just going to say increase in temperature, and since now it's warming up in here, that's a good example of my Q dot leaving. So I added work. This is actually called work in. I put work in and energy came out. So if I were to do my first law energy balance on this simple system, I would say energy in equals energy out, or I'd say energy in minus energy out is always equal to 0, because energy can't be created or destroyed. It can only change form. And the energy that went in was work, and it changed its form to heat energy, and the sum of that is 0. So therefore, the amount of work that went in is the same amount of heat energy that went out. This is just energy and energy. This is work energy equals heat. Are they the same amount? Yes. How can work be the same as heat? Well, they're both energies. They are both things that can be calculated in joules. So the number of joules of work energy that went in from mixing the system is the number of joules of heat energy that went out. So I'm going a little bit forward. Really, what I wanted to show you is what a closed system looks like and what the boundary looks like in a closed system. But this is what the first law energy balance looks like in that closed system. So this one was a solid boundary. This one was solid, non-moving boundary. Far more interesting is a moving boundary, like a reciprocating cylinder. Far more interesting is a reciprocating cylinder. So here I have a volume. I have a volume 1 and I have a volume 2, and volume 2 is greater than volume 1. And oh, it looks like in this system we added some energy. It looks like you put some Q dot inside here from a flame. That's definitely some heat energy doing it's adding heat over time. What is that heat doing over time? It looks like we kept the same mass. Mass didn't change. This is m dot equals 0, no mass flow. So if this is a mass of gas, this mass of gas looks bigger, must be heavier, right? No, because no more mass, no more gas came in. No gas went out. M dot equals 0, M dot equals 0. These are no flow. These are closed systems. Make sure that you know the difference between an open system and a closed system. If no mass flows, then this 2 kilograms of gas is the same weight, the same mass as this 2 kilograms of gas. Then what's going to happen? What's going to change? Well, ideal gas law. Ideal gas law says PV equals nRT. If the if the temperature is changing, then you must have a corresponding change in volume. So V2 is greater than V1 here. And then how do I form that into an energy equation? I had this energy equation for this problem. What's my energy equation for this problem? Well, something really cool is happening. E in equals E out. E in is Q dot. It's my heat energy. I don't have to do mass flow rate. I can divide it both sides by time. So Q equals the energy out. What's happening out? Well, think about work energy, force times distance. Force times distance. Look, something moved a distance. Distance D. Work equals force times distance D in Newton meters. This is really cool. So you actually did some work by pushing that piston up. And we know in a reciprocating engine that this actually does work, right? This translating motion up and down gets put on an offset cam and actually turns into a rotational motion. That's how internal combustion engines work. So our first law energy balance is that we add some heat to do some work here. This is much like a diesel engine, although the diesel engine compressed the gas in order to create the heat to do the work. So here you have 2 closed systems, 1 closed system, 2 closed system, the first law energy balance for 1 closed system and 2 closed systems. Quite interesting here. And that's what thermodynamics is about, being able to identify the boundaries, the system, and the surroundings, and what's going on thermodynamically as the energies change form from one side to another of those boundaries.